Hi everyone. Today we are talking about section 3.2 using second derivatives to classify maximum and minimum values and sketch graphs. So let's talk about what the second derivative is. An example that we've seen before was we talked about if we're driving in a car, the speed that we're going or the velocity is the rate of change of our position or the distance we've gone. So the first derivative of distance would be speed or velocity. Well, the second derivative would say, well, how is our speed changing? Well, that's our acceleration. So the second derivative is the rate of change of the derivative. Graphically, let's think about it. Say I've got a graph like this, a downward parabola. Remember, the derivative, first derivative, is the slope of the tangent line. So if I've got a tangent line here, it may have a slope, which remember is the first derivative, and maybe that's 2. But as I come over here, now maybe that derivative is 1. And then up here, the derivative is going to be 0. Down here, it might be -1, etc. And so if we look at those slopes, we see the slopes are getting smaller and smaller. And so if the slopes are getting smaller, what we call this graph, the shape of this is what we call concave down. And concave down is whenever the derivatives are getting smaller, which means the second derivative is less than 0. Or another way, the second derivative is negative. So it's concave down if the second derivative is negative. Similarly, we can look at an upward parabola and look at those slopes, and maybe this slope here, maybe that derivative or the slope, remember that's what that is, slope of the tangent line, maybe that's -2. And then over here, maybe it's 0. And then here, maybe it's 1. So we see the slopes are getting bigger, or the second derivative is positive because the rate of change of the slopes is positive. So we're going to call this concave up. And that's whenever the second derivative is greater than 0. Or we could just write f double prime is positive. So that's what we're going to look at. And that's what we're basing everything on. Now, don't get confused. Like, for instance, this upward parabola, it's concave up, but it's concave up the entire way. Not just, it doesn't have to be an entire parabola to be a concave up. For instance, think of an exponential graph. Here's maybe the graph of y equals e to the x. Now that graph is concave up as well, even though it doesn't go up on both sides like a parabola does. But that's still going to be concave up. Notice in this case, the entire time of that graph, the first derivative is going to be positive because the graph's going up to increasing. And the second derivative is going to be positive because the slopes are going up, up, faster and faster. It's concave up. In this case over here, I might be able to cut this right here. Over here on this side, the first derivative, the graph's going down, so it's negative, but it's concave up, so the second derivative was positive. And then once I cross the center line here, now the graph's going up, so now the first derivative is positive, and the second derivative is also positive. So it's increasing and concave up. And then, of course, we can do something similar on this first one over here, where we say, okay, the derivative is positive because it's going up on the left-hand side, but it's concave down, so the second derivative is negative. And then on the right, now it's going down, so the first derivative is negative, and the second derivative is also negative because it's concave down. So that's just an idea to get us going. Let's look at a couple of graphs, and then we'll actually do some problems. We'll talk about max and mins and some other things. Okay, so let's move from there. Let me slide this up and out of the way. So I've got a problem. I'm just going to paste it on here. They show us in the book a little graph. And it says, nice try. So let's go get it. Let's see if we can just go grab it. So it's right in here. See, I've got 4 problems for us today. We'll just try to copy it right out of there, paste it back in. Now let's see if it'll let us paste it. All right, so there's a graph. And in the book, the question says, identify the points of inflection. We haven't talked about that yet, but we will in this picture. And the intervals where the function is concave up or concave down. So notice, if we look at this graph, let me highlight this in, well, we'll start in black. If I look at this part of the graph, it's concave up, concave up, concave up. About there, it starts to flip, and then it's concave down. So right at this point, right at x equals 1, so if I go from negative infinity to 1, the graph in that case is concave up. Now we know that means the second derivative is positive, but look where it's still red from 1 and then forever going to the right. We'll say to infinity, it's concave down. So in that case, this second derivative is going to be negative. And again, your teacher, someplace in the book, someplace online problems, they may write that as greater than 0 for the positive and less than 0 for the negatives. I like the positive and negatives because when we check values, it's easier to see if it's positive or negative. We just look at the signs. So that brings up an issue though. An inflection point is where the graph or the function changes concavity. And so in this case, we see 1, we see that y value is 2. So at x equals 1, y equals 2, we have an inflection point on this graph. So that would have been the answer to what they have in the book is A. This would be the answer to what they have for B. But that's the idea. Now notice with inflection point, that's not 2 x values. That's not an interval of numbers. That's actually the x and the y value. So that's a point on the graph. With the concavity, that's an interval of values. So those are both x values. Obviously negative infinity or infinity aren't x values, but they are the concept that the x value is going forever to the left or forever to the right, depending on the sign with the infinity. Okay. Let's go grab another one of these and do a similar thing. So we'll just grab this one real quickly. Let's see. So we'll copy that. We'll come back in, paste it in. All right. So here's another graph. Same idea. Now, if we look at this and we say, hey, is this concave up or concave down? We see in the middle of the graph, it looks like it's concave down. It's a downward parabola. But it doesn't keep going down. It starts to flatten out as you go to the outsides. And in fact, at about here and about here, you know what? I think the value is about here and about here. At those two values, it looks like we're changing concavity. Because look to the left of this first dot. If I look, oh, I still the eraser on. If I look from here to the left, that's all concave up. And if I look from the right of this dot and I look up, that's all concave up as well. So in this case, we could say, oh, concave up, well, negative infinity until we get to about x is negative 1. But also starting x is positive 1 and then forever to the right, it's concave up again. In the middle, it's concave down. So that's from x equals negative 1 to x equals positive 1. Remember, those are both x values. So that's our concavity. But obviously, if it changed concavity, it has to have inflection points. And it changed concavity twice. So in this case, there's 2 inflection points. One is going to be when x is -1 and the y value is 2. And the other one's when the x value is 1 and the y value is 2. So 2 inflection points, which makes sense because we have 3 places where 3 different intervals of concavity. So it changed twice. We have to have 2 inflection points. So that's the idea. It's kind of easy to get to when we see the picture. Let's look at some facts that they give us about the function, the derivative, the second derivative, and let's try to draw the picture ourselves. So let's do this. And as before, when it gives us some of these, there's going to be various correct answers to it. We will just put one potential correct answer. All right, so let's go in here. We're going to paste this in. So here's what they tell us. Now let me read the instructions out of the book. It says, sketch a graph that possesses the characteristics listed. Answers may vary. Now usually they don't give you an answer in the back of the book, which is unfortunate. I think they should say at least, here's one possible answer. But I don't think they do, so you'll have to refer to this. Now, let's talk about this for a minute. Notice it gives us f prime of -1, f double prime of -1, and f of -1. First of all, let's list what's happening. So remember, if we get f of x, that's the original function, that's the y value, just like it always has been. Remember, y equals f of x. I'm going to clean that u up a little bit. So the original function is the y value. Well, what's the first derivative? Well, remember, that's the slope of the tangent line. We use that to determine whether the function's increasing or decreasing. That doesn't look much like a C, does it? We'll clean that up in case you're looking at that, trying to figure out what I wrote. So the original function, that's the y value. The first derivative is the slope of the tangent line. That tells you if it's increasing or decreasing. The second derivative is concavity. So remember those 3 things. So when we look at this graph and it tells us, hey, f prime of -1 is 0, well, that means the slope of the tangent line is horizontal. That means it's maybe the top or bottom of like a parabola looking piece. Might be an inflection point, but all we know at that point, at x equals -1, the graph has a horizontal tangent line. When it says f double prime of -1 is greater than 0, remember the second derivative, that's concavity. If it's greater than 0, concave up. And f of -1 is -5. That says when x is -1, y is -5. That's actually a point on the graph. So we know the graph has to go through that point. Similarly, f prime of 7 is 0. So again, there's a horizontal tangent line. F double prime of 7 is less than 0, concave down. And f of 7 is 10. That's the point, 7, 10. They also tell us f double prime of 3 is 0. We haven't talked about this, but think about it. If a positive number makes your graph concave up and a negative value makes your graph concave down, well, the number in between positives and negatives, of course, are 0. That's going to have to be where it changes inflection, changes concavity. That's an inflection point. Now, we're not guaranteed that it's an inflection point, but you can't have an inflection point unless the second derivative is 0 or undefined. Now, we already knew that it changed concavity because we went from concave up to concave down. So that has to be the inflection point. And then an f of 3 is 0. That's the original function. So that's my y value is 2. I think I said 0, but f of 3 is 2. So that's the point 3, 2. So now we can graph this. So let's see. We've got our graph. We have interesting things happen at -1, at 3, and 7. All right, so those are X values. We know it goes through -1, -5. So let's start with a point down here, -1, -5. We also know it goes through 3, 2. And we also know it goes through 7, 10. All right, so plot the points first. Now go to the first derivative. At -1, we have a horizontal tangent line. At f prime or at 7, we have a horizontal tangent line as well. Well, at 3, 2, that was an inflection point. So look, we know it's concave up at -1. So the graph has to be concave up. Am I going to get this to be concave up all the way until I get to 3? And then it changes to concave down. I didn't mean to erase that. How'd that happen? Here, let's start this graph over. See if I can get a better graph. Okay. So it's concave up, and then it gets to 3, 2, and it changes to concave down. Goes through there. There's my graph. Satisfied all the requirements. It goes through -1, -5, 3, 2, 7, 10. Had a horizontal tangent line at -1, -5, and 7, 10. Was concave up at x equals -1, concave down at x equals 7, and it changed concavity at x equals 3. So that's the graph. It has to satisfy all those requirements. And so this one does. There's not a lot of variation that you can have in this graph other than changing kind of how steep things are going, things like that. But that's essentially what your graph should look like. All right, let's try one more of these. Make sure that we have a fairly good handle on that. So let's move that out of the way. And I'm going to go pull in the other one. So this is our last thing that I'm going to copy and paste. And then we'll do some problems. Okay. So let's paste this one in. All right. So it tells us a bunch of things this time. Let's go through and figure it out. So f of -1 is 0. Okay. So again, horizontal tangent line. F double prime of -1 greater than 0. The slopes are increasing. That means it's concave up. And f of -1 is -2. So it goes through the point -1, -2. F prime of 1 is 0, horizontal tangent line. F double prime of 1 is greater than 0, concave up. F of 1 is -2, that's a point, 1, -2. F prime of 0 is 0. F double prime of 0 is less than 0, so that's concave down. And it goes through the point 0, 0. All right, let's see if we can figure this one out. Now, notice the x values they give us, -1, 1, and 0. So let's make it a little bit bigger scale-wise. Don't just scrunch them all in right next to each other. All right, so let's see. Let's start with the points. It goes through -1, -2. It goes through 1, -2. And it goes through 0, 0. All right, now let's figure out what's going on. We've got a horizontal tangent line here and here and here. To the left, it's concave up. To the right, it's concave up. And at 0, it's concave down. So the graph has to look like this. The graph comes down, it's concave up, concave up. Someplace over here, it's going to have to change because it's concave down when you get to 0. And then it changes again back to concave up by the time you get over here. And so the graph's going to look something like this. So it looks like a W, and that's our graph. So make sure you go through the correct XY points and then just check your increasing, decreasing, or horizontal tangent lines, and then make sure your concavity matches. But that's a graph that matches that. Okay, let's go in and actually do some problems now. So we've talked about inflection points. There's actually something called the second derivative test. We can use, well, we can look at this picture right here. Notice something on this picture. Right here and right here, we have relative minimums on that graph. Remember, we learned in the last section, we have a relative minimum if it's the lowest value in some interval, which this one is. So we've got relative minimums there. But notice -1 and +1 were both critical values because the derivative was 0, but also they were both concave up there. And so the second derivative test says, hey, if you've got a critical value and the graph's concave up at that point, it's got to be a relative minimum. And let's write that down. So this is called, here we use the black bin for this. This is called the second derivative test. Or we could just call it the F double prime test. All right, and it's going to tell us two things. At any critical value, remember that means the derivative was 0 or undefined. At a critical value, let's call it a critical point. I like that better. Let's move this up a little. At a critical point, the only difference between critical value and critical value is the x value. Critical point is that x value that's the critical value plus the y value, which makes it an xy point. So at a critical point, if f double prime is, well, let's do the one that we see, greater than 0, positive, there is, it's not very good writing, is it? A relative minimum. And just think of what the graph looks like at that critical point. And I'll abbreviate this next one because let's go back to the graph. Notice up here at 0, 0, we had a critical value, but it was concave down. We ended up with a relative maximum, the largest point in some interval. So we'll go state that at critical point, if f double prime is less than 0 or negative, there is relative maximum. All right, and we'll use that as we do these next couple problems, because we've got some problems. I've picked out 3 problems where they ask us to find, the book actually asks us to find increasing, decreasing first derivative. I don't want to make this problem overly difficult, so we're going to do the last part of the problem where it says find where the function's concave up or concave down and any inflection points. We will also use the second derivative test to see if we have a relative maximum or minimum. Okay, so let's see. So the first problem I picked out is problem 8, and they give us a function g of x is equal to x squared plus 12x minus 4. Find, well, let's do this. Find relative extrema. Remember that means max or min. Concavity and inflection points. All right, so let's go through this. We'll do a few examples. So the first thing I do is I take the derivative. G prime of x is 2x plus 12. If I set that equal to 0, 2x equals negative 12, divide by 2, x equals negative 6. I have one critical value. Let's look at that critical value and see what's happening. If I do g double prime of x, and I'm taking the second derivative, I just get 2. And so remember, what I'm doing is I'm going to plug in my critical value, negative 6. G double prime of negative 6. Well, notice there's no place to plug in the negative 6. I just get 2, which is greater than 0, which is positive. So it tells me the graph is concave up. That's not how you spell concave, is it? Concave up. Well, if the graph's concave up and it's a critical value, that has to be a minimum. Therefore, relative minimum at x equals negative 6. Now we can find out what that point is. We can say, oh, the y value, remember that's plugging the negative 6 into the original function. Oops, I said f, this is the g function, isn't it? G of negative 6, well, g, what, x squared plus 12x minus 4? X squared plus 12x minus 4. Did I write that down right? Yeah. All right, so let's see. I'm just going to plug this in my calculator, because what are we going to have? We're going to have 36 minus, that's just 72, isn't it? Minus 4. Negative 40. So I can say relative min equals negative 6 comma negative 40. That's the point where my relative minimum is. Now, notice my g double prime. Let's go back here. G double prime was 2. It's a constant 2. It's always greater than 0. It's always positive. That means the graph is always concave up. G of x is always concave up. So down here, we'll write this. We'll write concave up, negative infinity to infinity. And we know that because the graph x squared, we know that's an upward parabola. Doesn't change concavity. Since it's always the same concavity, it never changes concavity, no inflection points. So there's the other two ideas. And then we're done with that problem. On the next problem, we'll show what we need to do if we do have some other points, if it changes concavity. All right, so let's try another one of these, problem 14. Again, it's g of x. This one says x cubed minus 48x minus 1. Same question. I guess I don't need that piece right there because that's not how I wrote it before. So same question, find concavity, find relative max or min. So I take the derivative, 3x squared minus 48. I'll set it equal to 0 to find critical values. So 3x squared equals 48. Divide by 12. I mean, divide by 3. I don't know where that divide by 12 came in. 48 divided by 3 is 16. And then remember, if I'm going to take the square root, anytime I take the square root, I have to say plus or minus. So I'm going to get two answers, either x equals positive 4 or negative 4. Now what I'm going to do is this. Let's go, and I'm not going to do the first derivative test. I'm not going to talk about increasing, decreasing. Let's not do that. We learned that in the last section. Let's look at, we're going to use those. Those are my critical values. But let's go to the second derivative. And I'm going to do this. The second derivative, g double prime of x. Well, we can see the derivative right up there. So the second derivative is just 6x. Set it equal to 0. Divide by 6, I get x equals 0. There's only one place where the second derivative is 0. So what I'm going to do is I'm going to look to the left and right of 0. So notice this is going to give us the interval negative infinity to 0. This is going to give us 0 to infinity. I'm going to take a test number in each of those intervals, say -1 and +1. I'm plugging them into the second derivative because I'm looking for concavity. Well, if I plug in -1, g prime of -1 is 6 times -1, which is -6. Negative, notice that's less than 0. This is what I like, though. Look, it's negative. So since it's negative, that's what I was concerned with. And if I plug in 1, I'm going to get positive, of course. 6 times 1. So you could say greater than 0. You could say positive, whichever way you want. I put a positive up here is why I like the negative and the positive. But what does that tell me? It tells me that the original graph G, I really like the way that came out. The original graph G is concave down and then it's concave up. Now I can answer those questions about concavity. So let's say this. Concave up, 0 to infinity. Concave down, negative infinity to 0. Since it changed concavity, we have an inflection point. The inflection point is at x equals 0, but we need the y value. Well, go back to the original function, x cubed minus 48x minus 1. If I plug in 0 for x, I'm going to get -1. So that's my y value of my inflection point. Now that value came from g of 0, which was, what did we say it was? X cubed minus 48x. 0 cubed minus 48 times 0 minus 1 equals -1. That was my y value. That's where that came from. So that answers all the concavity questions. Let's go back and use these two critical values to find out if we had any relative max or relative min values. So here's back to the second derivative test. So let's go, we'll call it F double prime test. Remember, I should call that G double prime, shouldn't I? G double prime test. Well, G double prime was 6x. So G double prime. Now let's plug in the -4, and I get 6 times -4, which is -24. I don't care that it's 24. I just care that it's negative. Because what that tells me, I already know that's a critical value at -4. If the second derivative's negative, it's concave down. Therefore, those 3 dots in a triangle mean therefore, relative maximum at x equals -4. Now again, if you need that as a point, you need to plug that into the original function to find the y value, like we did with the inflection point. I'm just going to leave it here for now. And then if we do G double prime of +4, I get 6 times +4, which is +24, meaning it's concave up, therefore it's a relative minimum. We can see from the graph, there's a lowest point. Again, you may need to find the y value, depending on how they're asking the question, but I've identified it real quickly. The second derivative test is really nice if it's easy to take the second derivative. With polynomials, really nice. If you had to do, say, the quotient rule, you've got all that stuff on top and now the bottom squared. Well, to take the second derivative of a quotient rule, now you need to do the quotient rule again, plus you need to do the chain rule on the bottom because it's a whole function squared. It's a mess. In that case, I wouldn't use the second derivative test at all to test for relative max or min. If I wanted concavity, I still have to do the second derivative. But I'm going to stay away from the second derivative if they're just asking relative max, relative min. All right, let's do one more of these. Again, and I picked a polynomial just to get the idea down. When we go to later sections, I'll pick other types of functions. But at this point, I want the math to be easier so that we understand the ideas of the second derivative. But don't worry, there's plenty of stuff coming up later. J of x, it's not a very good J, but it's okay. 3x to the fourth plus 4x to the third. All right, again, we'll look for concavity, we'll look for any inflection points, and we'll look for any relative extrema. So as always, start with the first derivative, 12x to the third plus 12x squared. Set it equal to 0. Remember, if you have x in two different places at different powers, you have to have the function set equal to 0 and factor. I'll have students that don't want to factor things, so they add a constant to both sides. You can't do that. It has to be equal to 0, or else it does you no good to factor. The greatest common factor here is 12x squared. If I factor that out, I get x plus 1. Set each of those factors equal to 0. That's why we have it set equal to 0. It's the property of zero products. Well, this only happens, you can divide by 12 and take the square root if you want to, but the only thing that's going to make that 0 is 0. I'll just do it real quickly so we see it. X squared equals 0. Take the square root, plus or minus. Well, the square root of 0 is 0. Positive 0, negative 0, it's still 0. And here we subtract 1. X equals negative 1. Those are our two critical values. All right, that's all good and well. We're going to use those to find relative extrema, but not yet. Because what I want to do is I want to find, we need to be able to see the first derivative. I want to find concavity. So I'm looking at the second derivative. Let's see, 12x to the third is going to give me 36x squared plus 24x. Set that equal to 0. Factor that out. I can factor out a 12x, common factor. Leaves me with 3x plus 2 equals 0. Well, the 12x equals 0, divide by 12, x equals 0. 3x plus 2 equals 0, subtract 2, divide by 3. Again, I have two critical values. They're critical values for the second derivative. They may be where we change concavity is what they're going to represent. So I have to put them in here, negative 2/3 and 0. And I look to the left, negative infinity to negative 2/3. I look in between this time, since I have two of them, negative 2/3 to 0. And I look to the right, 0 to infinity. And I'll test a number in each of those intervals. So let's go negative 1. Now between negative 2/3 and 0, we don't have a, let's put in 0.1. Make it negative, of course, because it's to the left. That'll be an easy thing to check. And then we'll plug in positive 1 over here. Okay, we're plugging them into the second derivative. Now, I'll tell you what I do. I plug them into where I have it factored out. Because remember, that's the second derivative right here. But it's factored because all I care about is the sign. Think about what I'm doing when I plug in the negative 1. If I do 12 times negative 1, I know that's a negative number. If I do 3 times negative 1 plus 2, that's negative 3 plus 2, that's negative 1. That's also a negative number. If I have a negative times a negative, that's a positive. So I just do that in my head and I say, hey, the second derivative is positive there, which tells me the function itself is concave up. Now I'm going to do the same thing with negative 0.1 and just think of the signs. So if I do j double prime of negative 0.1, sign-wise, 12 times negative 0.1 is negative. 3 times negative 0.1 is 0.3, negative 0.3 plus 2, 1.7, positive. Well, a negative times a positive is a negative. Oh, it's concave down. And then I do the same thing with j double prime of 1. 12 times 1 is positive. 3 times 1 plus 2 is also positive. Multiply those together, I get a positive. Oh, it's concave up. But I can do that in my head if I look at where it's factored. You can always go back to where it's not factored and plug it in and actually use your calculator and see if it's positive or negative. But I find it, if it's factorable, to do it there and just look at the signs. So I don't care about the number, I just care if it's positive or negative. And so I can answer my question right there for concavity. I'm going to slide it up here because I had a little bit of room up here. So let's say concave up, let's see, negative infinity to negative 2/3, but also 0 to infinity. Concave down, negative 2/3 to 0. Inflection points, there's two of them because it changed concavity twice. One was at negative 2/3 comma something, and the other one's going to be at 0 comma something. Let's figure out what those are. Let's go back to the original function. If I plug in 0, that'll be easy enough. 0 is going to give me 0. Going back to j of x, 3 times 0 to the 4th plus 4 times 0 to the 3rd, that's just 0. The negative 2/3, I'm going to have to figure these out. So this value here is going to come from the original function, j, of negative 2/3. And I'm just going to use my calculator to tell you what it is. So let's see. So I've got the original function. So it's 3 times, and then in parentheses, I'm plugging in negative 2 divided by 3, close that parentheses, raised to the 4th power, plus 4 parentheses, negative 2 divided by 3, close parentheses, raised to the 3rd power. Is that what that says? Yeah. And I get negative 0.592592 repeating, but on my calculator, I'm just going to go math, turn it into a fraction for me. It's negative 16/27. Negative 16/27. So those are my values. I've got 2 intervals where it's concave up, 1 where it's concave down, and then 2 inflection points. Have to have 2 inflection points again for that same reason. But let's use these critical values to find if I have relative max or mins. Now, I will tell you, here's what I know. We'll go back up to that in a second. But notice it's concave up, concave down, concave up. What did I say? Up, down, up. It's concave up, concave down, oops, up, down, and then up again. So I know these have to be relative mins, and that has to be a relative max. Let's go see if that's true. Let's see, up, down, up. Oh, I only have 2 critical values. All right, so let's see what's happening. So 0 and negative 1. Okay. So if I do j double prime of negative 1, not negative 1, what were my critical values? 0 and negative 1. Yeah, negative 1's my first one. So j double prime, 36x squared plus 24x. Let's just call this one x since I plugged x's in. So j double prime of negative 1, 36 times negative 1 squared plus 24 times negative 1. Well, the negative 1 squared is going to make it positive, so it's going to be 36 minus 24, it's 12. But greater than 0, positive. Well, what does that mean? At negative 1, it was concave up. So I have a relative min at x equals negative 1. And then I do, not j, I mean j, not g. J double prime of 0 which is 36 times 0 squared plus 24 times 0 equals 0, that's not positive or negative. So actually what happens at 0 is I can't use the second derivative test. I would have to use the first derivative test there to see if it's a relative max or relative min or just an inflection point. Remember, it was just an inflection point. So we could look to the left and right of 0. I'm not going to, because we're not going to go there. But that's the idea of that problem. So let's say this. Recall inflection point, neither max nor min. All right, we already saw that there was an inflection point at 0. So anyway, that's the idea of this problem. We learn in this section, second derivative tells us concavity. Positive second derivative, concave up. We might have a relative min there if it's a critical value. Negative second derivative, concave down, would give us a relative max at a critical value. And an inflection point is where it changes concavity. All right, so anyway, I will show you later when we're doing some application problems that oftentimes using the second derivative test is a real quick way to verify that you have relative max or relative min. And we'll see that coming up in the next section. All right, that's all for today. This takes practice, understood, but the more practice you do, the better you'll get, and just keep working at it. And I'll talk to you again soon.